Hello! In this video, we're going to be talking about the squeeze theorem, which is used to figure out the limit of functions who are really not behaving themselves, but we can squeeze through two other functions who are behaving in order to find their limit. So, what the squeeze theorem states is if you've got two good functions that you can find the limit of, and then this misbehaving functions that's crammed in the middle of those two, then if these two limits are the same, and then hey, guess what? That one that's stuck in the middle, it also has to have that same limit. Here's an example of when the squeeze theorem might be applied. I have the absolute value of cosine of x, which really just doesn't behave. It does all these wobbles. It's a really unpredictable function. However, it is stuck between these two very simple functions, the absolute value of x and the absolute value of negative x. You can see how it just touches those two, but never really goes outside of it. If later it did, that's fine, but I'm only concerned about this area right here where it is 0, since it's kind of stuck in between those two, and these two, the limit as x approaches 0 of the absolute value of x, and the limit as x approaches 0 of the negative absolute value of x, are both 0. We can say with confidence that this limit as x approaches 0 of the absolute value of x, cosine of x, has to be 0 because those two top and bottom functions are meeting right the middle. The only way that the absolute value of x cosine of x can make it through there to squeeze through that gap is if its limit is also 0. In order to be able to apply this theorem, you need to make sure that you clearly state that the hypothesis of the squeeze theorem has been met. So you first demonstrate that the two functions squeeze the middle function. You find the limits of the outside functions, confirm that those two limits are equal, and then state the theorem and answer. Let's try applying the squeeze theorem to some function I don't even know. It could be doing all kinds of crazy things, but I still want to be able to find out its limit. We've already been given the first step. It's right here that f of x is stuck between these two other functions. So I can move on to step 2 and check their limits. If I start with the smaller one, the limit as x approaches a of b minus the absolute value of x minus a, this thing I can just direct substitute into that, no problem. So that's b minus the absolute value of a minus a. Well, a minus a, that's just 0, so this thing is heading towards just b. Whatever b is, I don't really know, but I don't care. It's just heading towards something. Hopefully, this thing will have an identical limit. As I check the other side, the limit as x approaches a of b plus the absolute value of x minus a. Again, I can direct substitute in. So I get b plus the absolute value of a minus a. Oh, hey, that's 0 again. They're b. Sweet. So I can move on to my third step. Are those two things equal? Yes. B is equal to b. Since those two things are equal, I can apply the squeeze theorem. And I do need to state that I am using the squeeze theorem. After doing those mathematical computations, I would say, therefore, by the squeeze theorem, the limit as x approaches a of f of x has to equal b. I don't even know what f is, but I do know that its limit should be identical to those other two limits. In this example, we want to again find the limit graphically. So if I look at this graph, I can see, oh man, that thing is really misbehaving, but it is heading towards 0. So I want to check what's going to be going on compared to these two functions. Notice that I just got rid of that sign, the kind of riffraff at the end that I don't really know what to do with, and I kept this x squared. So I first need to demonstrate, okay, well, why is this green function stuck between the red and the blue? Let's begin with the positive one because it's a little bit easier. So I might say, hey, well, I know this thing has to be less than this. This value of sine is never going to be bigger than 1. It can be less than 1. It can't go any deeper than -1, but whatever I have here is always going to be smaller than this value. And if I'm multiplying by a smaller value, this thing has to be the smaller thing because this is the bigger number, even though it's just a 1. Okay, but if you multiply these two things together, that's just x squared. So that means that x squared sine 1 over garbage has got to be less than x squared. First part done. Now I have to deal with, okay, why is the green one always going to be bigger than the red one? Okay. So in that case, let's just stick a negative on front of this thing because then we know that this thing, the thing that we already know about, it's got to be bigger than if you put a negative in front of it. If you put a negative on stuff, it's definitely smaller than its positive version. Okay. Then can we do a trick like this again? All right. Well, if I am multiplying by something, if I've got a negative version of it, if I have a smaller number here, a smaller number here, less negative is going to be bigger. So less negative over here is going to be bigger than more negative over here. If that makes sense. Hopefully you can kind of follow that. It's a good opportunity to pause the video and make sure like, ooh, I can follow what's going on there. Since that's true, then I can say, okay, well, then this has to be negative x squared has to be smaller than x squared sine garbage. Cool. So at this point, we know that the green function is squeezed between our negative x squared and our positive x squared. Now that we have completed step one, we have to figure out what is the limit of our outside functions. Fortunately, finding the limits of those outside functions is easy peasy since we can direct substitute. The limit as x approaches 0 of x squared, that is just going to be 0 squared, which is 0. And the limit as x is approaching 0 of negative x squared is, hey, negative 0 squared, which is also 0. And hey, those two things are equal. So we can say that the limit as x approaches 0 of x squared equals the limit as x approaches 0 of negative x squared, and they both equal 0. We've demonstrated our squeeze, we've checked our two limits, we've confirmed that they're equal, we have met the criteria for the squeeze theorem, and now we are able to state, hey, we can use the squeeze theorem. By the squeeze theorem, state your theorem, we can say that the limit of this function that we couldn't figure out has to be 0. Thanks, squeeze theorem. And that's it about the squeeze theorem. Make sure when you're using that squeeze theorem that you confirm that hypothesis. If you just say, by the squeeze theorem, it's got to be this, that's no good. You need to go through those steps of showing why you can apply the squeeze theorem. Make sure you squeeze the middle, check the limits of your outsides, make sure that they're equal, and then state which theorem you are using. Thanks for watching. Bye-bye.